Good day, doctors. This will be your lecture for osteogenesis under the bone topic in your histology class. The objectives of this lecture is for you to illustrate general structure of the bone, classify types of bone tissue, identify the cells of the bone tissue, and discuss and understand the process of bone formation and bone repair. Generally, the bones are organs of the skeletal system, and the structural components of the bones are generally called the bone tissue. So we can classify bone tissue into two major types, either the dense or the compact, as you know, or the spongy, and also termed as the cancellous bone. So they are also classified according to shape, where we can identify them depending on their shape, and the location of those two types of bone tissue can depend on what type of shape the bone is. So typically, if you will cut a bone, you will notice two distinct structural arrangements, and those are referred to as the compact bone and the spongy bone. So these types of bone tissues can be recognized and by their name, compact, that appears as a dense structure of bony tissue, and the spongy tissue will appear as a meshwork of continuous bone, and most of that is covered, occupied by bone marrow and also blood vessels. So we can also classify bones according to the shape, and also the location of the two structural types of bone tissue will vary on the type of the bone shape. So we have long bones, the short bones, the flat bones, and the irregular bones. So their characteristics are representative of their name. So the long bones are generally long, so they are longer in one dimension, and the other dimension are way shorter compared to the longest dimension. And a long bone usually consists of a shaft and two ends. So the two ends of a long bone appears like this, and the shaft will appear as a hollow tube. So there is another type of bone shape that is a short bone. So this appears somehow nearly equal in length and diameter. And the flat bones are just thin and plate-like. So example of flat bones are your sternum and the skull cover. So the flat bones also consist of two layers of a compact bone, which appears like this, and an intervening layer of spongy bone that looks like this. So the irregular bones are irregular because the shape does not fall on these three categories, and the shape can be complex, as you can observe, for example, in the vertebra and the ethmoid bone. So those are the types of bones according to shape. In the characteristics of bone um, tissue of the long bones in terms of schematic representation will look like this. So the long bones will have a shaft, or also called the diaphysis, here, and two expanded ends here, and they are referred to as the epiphysis. And before the diaphysis will transition into an epiphysis, usually there is a um, expansion that before the epiphysis, the part, so that is the metaphysis. So that is a flared portion of the bone between these two structures. and that metaphysis will extend from the diaphysis to the epiphyseal line, this one. And the diaphysis or the shaft will high likely contain a hollow or a cavity that contains the bone marrow. So this part, the hollow cavity here, is also referred to as the medullary cavity because it forms the inner portion of the bone. So in this part, the shaft, the inner or the entire thickness of the bone here is compact, but the inside or the internal part is composed of a small amount of spongy bone which contains the or faces the marrow cavity. So in the other part, the epiphysis, this composed mainly of the spongy bone and on only a thin layer of compact bone, which serves as the outer shell. So for short bones, it will mostly possess a shell of compact bone like this and have a spongy bone inside, which also contains a marrow or medullary cavity. So the short bones can be found on movable joints, and the short bones usually articulate with another bone. So as the general cover of the bone structure, there will be a layer we termed as the periosteum. So this one. However, for parts of the bone like this that serves as an articular surface, meaning it connects to another structure, it does not cover, the periosteum will not cover this part. Instead, it will be covered by a fibrous, um, it will be covered by an articular cartilage. So the periosteum will end before the part that articulates with another surface. So generally, the periosteum is a connective tissue that covers the outer surface of the bone, except for the parts that articulates with another structure, because those parts will be lined or covered by an articular cartilage, which falls as a hyaline cartilage. So this is a schematic overview of the basic features of the bone. So there are three cell types that you can observe here. There is an osteocyte, there is also an osteoclast, and also an osteoblast. So these three cells are the three main cell types of the bone. So this is a section in the humerus, and this represents the typical lamellar organization of bone. So here you can see representation of the osteoblasts, and they usually secrete matrix, and this will harden by classification. So while it secretes matrix, there will be trapping of different cells inside, referred to as the one of those cells are the osteocytes, and also there can be noted osteoclast. So the osteocytes will maintain the matrix calcified, and they will also receive nutrients from the minor vasculature here in the central canals of the osteons. So there are small channels that will communicate, you will see here. So those are the small channels and they are referred to as the canaliculi. So they will interconnect each structure from one another. So you can note that there are different um, groups of lamellae, and each unit here that contains a central canal, a perforating canal, and concentric lamellae. So that is referred to as the osteon. So the periosteum, the connective tissue we mentioned earlier, that will cover the entirety of the bone. But the endosteum will cover the trabeculae, and they are surrounding the marrow cavities. So this is representation of the cancellous bone, and when you magnify them you can note the presence of the three major types of bone cells, and the spaces in between are for the bone marrow. So this is how the periosteum will appear. So the periosteum will contain two major layers. So the outer fibrous layer, sorry, this is how the periosteum will appear under the microscope. So you can notice two distinct layers, the layer of dense, irregular connective tissue that covers the outside of the bone, and this is the outer fibrous layer, and in the internal part, that is the inner osteogenic layer, which contains progenitor cells, and the progenitor cells will differentiate into the osteoblasts. So those osteoblasts are a type of bone cell that are responsible for increasing the width of the bones. So this is a larger view. So this is the dense, irregular connective tissue that contains the fibroblasts. So the fibroblasts usually produce a type 1 collagen on the outer surface of the periosteum, and the progenitor cells are located mostly here. So this is a bone tissue. So let's go to the different types of cells tissue. So we have the osteoblasts, the osteocytes, the osteoclasts. So these are the three major types of cells of the bone tissue. And we also have the osteoprogenitor cells and the bone lining cells. So this is a table that represents the different types of cells of the bone tissue. So you have the osteoblast, osteocyte, and the osteoclast. So in terms of location, the osteoblasts are generally found on bone surface, and they form a layer, and sometimes they are also found in the closing cones of resorption canals, while the osteocytes are found in the lacuna and canaliculi of bone matrix, as you can observe in the previous slide. And osteoclasts are found also on the bone surface, but they, instead of close the cone of resorption canals like the osteoblasts do, they cut the cone of resorption canals. In terms of percentage, majority of the cells are composed of osteocyte, and then osteoblast, and then osteoclasts. So by their term, osteoblast and osteoclast, you can deduce their function that the osteoblast is mainly responsible for mineralization, while the osteoclasts are responsible for hydrolysis of the mineralized bone matrix. And the osteocytes, they maintain the bone matrix. So what are the precursor cells of each cell type? So the osteoblast mostly come from osteoprogenitor cell. Thus osteocyte can come from osteoblast, and the osteoclast is a type of cell that falls under hemopoietic cells. So um, this illustration, you can see the different layers of the locations of the bone cells. So the osteoblasts are usually in the surface, and the osteoid layer will be composed of different collagen fibers, and then eventually there will be formed mineralized bone. So they are the bone forming cells. So they synthesize and secrete the organic components of the matrix. So ano yung origin? Mesenchymal stem cells or osteoprogenitor cells, and they are found in the surfaces of bone matrix and are bound by integral proteins. So some will differentiate into osteocytes once the synthetic activity is completed. And as a secretory cell, the osteoblast secretes both type 1 collagen, you can see collagen fibers, and also bone matrix protein. So they will, this part, the secretions of the osteoblast, the type 1 collagen, and the bone matrix will constitute this layer, which we refer to as the osteoid layer or the osteoid. So these bone matrix proteins also include the BSP1 or the osteopontin and the BSP2. So those are bone sialoproteins, referred to also as multi-adhesive glycoproteins. And also, these bony proteins consist of osteocalcin and osteonectin, which are calcium binding proteins. So we know that osteoblasts are active when the alkaline phosphatase and the osteocalcin are in normal levels. So they are considered as markers of osteoblast activity. So when there is early mineralization around the vesicles, there will be a compact formation of that layer, and eventually when enough minerals or calcium has been incorporated to this layer, they will become the mineralized bone. So how do we recognize osteoblasts under the microscope? They usually appear as cuboidal or polygonal shape, and they usually aggregate into a single layer of cells that form on the surface of a forming bone. So when they release matrix, it's not initially calcified. So deeper into that layer, that is when the calcification or the mineralized matrix will be found. So this part, if we observe them under the microscope, since they are not immediately calcified, they will appear as light staining mineralized matrix, while the mineralized matrix will stain heavily with the eosine part of the H&E staining. Next cell of the bone tissue are the osteocytes. So the osteocytes are the cells that will maintain the bone matrix that was previously secreted by the osteoblast. So this is also a schematic diagram. So the osteocyte is considered as the mature bone cell, and the mature bone cell that is enclosed by a bone matrix that were from the osteoblast secretion. So you can see that the osteocytes are covered by bone tissue. So usually, di ba, sabi natin, the osteoblasts can turn into an osteocyte, and that process can last for about 3 days. During that time, there has been large amount of deposition of extracellular matrix by the osteoblast. And the osteocyte will develop several shape processes outside, like this, if you can notice as a representation of the illustration. So this osteocyte will occupy this space here that is referred to as the lacuna. So the lacuna, or the space here in the bone tissue or the bone matrix, will conform to the shape of the osteocyte. So um, these parts, the processes of the osteocytes are enclosed within the bone matrix, and sometimes those processes can also communicate with the neighboring osteocytes and bone lining cells through the part of the cell which are referred to as the gap junctions. So they are metabolically active, and they respond to mechanical forces that are applied to the bone. So that is the function of the osteocytes. So they are able to respond to mechanotransduction or mechanical stimulus. So when that happens, they can um, they can maintain the bone matrix. So if there is a bone that is um, subjected to a decreased mechanical stimuli, for example, there is a muscle weakness, or there is immobilization, or there is weightlessness if you are an astronaut. So that can respond to a lesser stimulus to the osteocyte. So it will also um, perform less in its function of maintaining the bone matrix. So decreased mechanical stimuli can also promote bone loss, while increased mechanical stimuli will promote bone formation because it responds to the need of the bone. So that's one of the main functions of the osteocytes. So we have three major types of osteocytes according to its functional states. So we have the quiescent or quiescent osteocytes, the formative osteocytes, and the resorptive osteocytes. So these functional states, they are they are classified according to the morphology of these cells, and they can also be identified based on their appearance under electron micrographs. So the quiescent or the quiescent osteocytes, in terms of appearance, they have a certain paucity of their rough endoplasmic reticulum and markedly diminished Golgi apparatus. So these um, morphology will represent a mature calcified matrix as seen in close opposition to its cell membrane. While the formative osteocytes, they will exhibit matrix deposition, and the rough endoplasmic reticulum and the Golgi apparatus are more abundant, and you can also notice evidence of osteoid in their periphery within their lacuna here. While the resorptive osteocytes, um, just like the formative osteocytes, also contain more endoplasmic reticulum and Golgi apparatus like the formative one compared to the quiescent, but in the resorptive osteocytes, through its name resorptive, it contains enzymatic vacuoles we term as the lysosomes. So that's the difference of the resorptive osteocytes with the formative osteocytes in terms of organelles. While the quiescent osteocytes, they contain less of the rough endoplasmic reticulum and less of the Golgi apparatus. And in terms of function, when there is degradation of bones by different metalloproteins that are secreted by resorptive osteocytes, they somehow uh, reflect the function of osteocytic remodeling. That's why the release of the metalloproteins by the resorptive osteocytes is also referred to as the osteocytic osteolysis. So that part, as a function of this type of osteocytes, that is responsible for the calcium and phosphate homeostasis na part of the bone. So generally, the osteocytes will live up to 10 to 20 years. So the lifespan of the osteocytes also represent somehow the bone age of the person. So if the percentage of the dead osteocytes are increasing, it means the bone age is also increasing. So at 1% at birth, it almost increases to 80% in the 80th decade of life. So that is how the percentage of dead osteocytes reflect old age. So the third type of bone tissue cells are the osteoclasts. So they are responsible for bone resorption. So in terms of morphology, they are large multinucleated cells, and they are found at sites where the bone is being removed. And they also rest directly in the bone tissue where bone resorption takes place. So the location of the osteoclast in the bone tissue is referred to as resorption lacunae or resorption bay, also termed as house ship lacunae, because of um, the appearance of the cell, which represents the osteoclast activity. So they are easily recognizable adjacent to the osteoclast. So the cell is very evident because of its large size and marked acidophilia if observed under the microscope. So they also represent marked or strong chemical reaction for acid phosphatase because they have lots of lysosome inside. That's why we use enzymes that contain tartrate-resistant acid phosphatase as a marker for osteoclast activity and their differentiation. So osteoclasts are derived from hemopoietic progenitor cells as mentioned earlier, and they transform or differentiate to an osteoclast by influence of different cytokines just like other hemoprogenitor cells. So they are not related to osteoblasts in terms of progenitor cells. So they are derived from the same progenitor cells, just like the granulocytes and the macrophage. So they belong to the same lineage. And the osteoclast will form close association with stromal cells in the bone marrow. Their close association with hemopoietic progenitor cells also respond to their response to the T cell stimulus. So since the osteoclast will express different transcription factors like CFOS and NF-kB or nuclear factor KB, so they also respond to the different rank molecules that are being secreted by the T cells. So this rank ligand and rank molecule signaling mechanism, this part here is essential for their differentiation and maturation. Plus the polypeptides that are also being produced by the osteoblast like the macrophage colony stimulating factor since they belong under the same progenitor as the common myeloid progenitor. So during inflammation, the activated T cells will also produce different molecules like soluble rank molecules and membrane-bound rank molecules. So when that happens, the osteoclast will respond to these molecules. That's why during inflammatory process, there can be an osteoclast-mediated bone resorption because they respond to those types of molecules. And this pathway can be blocked by the molecule osteoprotegerine. This one. So that the osteoclast will not be stimulated every time there is an inflammatory process. Now the new formed osteoclast, when they are still inactive, they have to go the activation process in order to undergo the bone resorption mechanism. So when that happens, when they are already activated, your osteoclast will have three distinct specialized region con that contribute to their function. So we can refer to them as the ruffled border, the clear zone or ceiling zone, and the basolateral region. So those three borders, I want you to look it up and differentiate those three. Now let's go to the other cells of the bone tissue, which do not belong to the three main types of bone tissue. So the bone lining cell, and these bone lining cells are derived from osteoblasts, and they cover bones that are not for remodeling. So they are just a flat layer of cells with an attenuated cytoplasm. You can see here. So these are the bone lining cells. So they are found on the external bone surfaces, and when they are found on external bone surfaces, they are termed as periosteal cells. But when they are found in inner lining of those bone surfaces, they are referred to as endosteal cells. So you can notice the presence of gap junctions here. So the gap junctions will serve as the communication between these cells. And remember, they are derived from osteoblasts. So before they were thought to function in maintaining and supporting the osteocytes nutritionally through regulating the movement of calcium and phosphate in and out of the bone. So that those are the bone lining cells. So these are electron micrograph illustrations of the gap junctions of these bone lining cells. So this is a general picture of the different cells of the bone tissue. So you can see here osteoblasts and osteoclasts will line bone surfaces, and the active osteoclasts will have a certain processes or ruffled border appearance here, meaning they are active in their bone resorption process, while the osteoblast will release bone matrix. The osteocytes will maintain those bone matrix released by the osteoblast, and the osteoprogenitor cells and the bone lining cells. So when external surface bone lining cells are referred to as periosteal cells, and when found in the internal layer, they are referred to as the endosteal cells. Now, so we have different types of bone. The woven bone, which are newly calcified bone, the lamellar bone, which are bone remodeled from woven bone, and the compact bone, which consists 80% of all lamellar bone, and cancellous bone, which consists of 20% of lamellar bones. So in terms of physiological features, the woven bone will appear as irregular and random, and they are lightly calcified, while the lamellar bone, they will consist of parallel bundles of collagen in thin layers and are heavily calcified. So the compact bone are densely packed osteons with interstitial lamellae, and the cancellous bone will consist of different spicules or trabeculae covered by the endosteum. So the woven bone, we refer to them as immature bone. The lamellar bone, we refer to them as the mature bone. The compact bone, We also call them as cortical bone, and the cancellous bone, we refer to them as the spongy bone, trabecular bone, or the medullary bone. So in the immature bone will display as an irregular organization. So um, they will appear as a non-lamellar bone, meaning a bundle bone. That's why it's termed as a woven bone. So they contain more cells per unit area than the mature bone. So the matrix of the immature bone has more ground substance than does the matrix of the mature bone. So the immature bone, as you can see in this slide, is not heavily mineralized when they are formed. So the mature bone, when they undergo secondary mineralization, that is more evident, and they are darkly staining compared to the immature bone. So the bone tissue initially formed in the skeleton of the developing fetus is called an immature bone. And the immature bone will form more rapidly than the mature bone. And you can see that during examination of radiographs. In the fetus, they have immature bone as the major bone type, and in the adult, the mature bone is the major bone type. The mature bone, you can see, has a lamellated structure. So they are composed of structural units here, referred to as the osteons. So also termed as the Haversian system. So there is a central canal that contains vessels, and those vessels will enter the marrow cavity and supply blood to the shaft of long bones, because the shaft does not have that inherent blood supply. So the blood supply to the bone tissue is essentially centrifugal. So you can see the different lamellated appearance of the mature bone. So this is an illustration or a diagram of a section of a compact bone. So the concentric lamellae and the Haversian canal that are being surrounded consist of the osteon. So you saw that in the um, previous slide. So one of the Haversian system here is fully examined. So this represents different bone sections. So you can see the several concentric lamellae that are partially removed to show that there is a perpendicular orientation of collagen fibers in the adjacent layers. So the interstitial lamellae that resulted from bone remodeling here is obvious in this illustration. So there are different layers of circumferential lamellae of the bone. So in the inner circumferential layer, those are this one. They are covered by the endosteum. So that endosteum will face the bone marrow surface, while the outer bone na part that is covered by the periosteum. So this is a thicker layer of connective tissue that covers the entire bone surface except for the parts that will articulate with another structure. So this is how um, a compact bone will appear in diagram. So in between osteons, so there are remnants of the concentric lamellae, so that those are the interstitial lamellae, and the perforating canals, or referred to as the Volkmann's canals. So these are channels in lamellar bone through which the blood vessels will travel from the periosteal and endosteal surface to reach the osteonal or Haversian canal. So notice that the Volkmann's canals are not surrounded by concentric lamellae. So that is obvious when you try to differentiate the Haversian canal versus the Volkmann's canal under the microscope. Perpendicular ang lamellae compared to the parallel in the in the Haversian canal. So this is how a lacunae here will appear under the microscope. So the concentric lamellae and the Haversian canal. So this is the Haversian canal, and this is parang the osteon or the Haversian system. So it consists of several concentric lamellae, and you can see the different lacunae that contains the osteocytes. So dito hindi natin masyadong nakikita yung example ng Volkmann's canal. What we see is the Haversian canal. This is another section of that view. So this is the circular opening that contains the different blood vessels here, pero hindi siya kita dito. So this is how a lamellar bone will appear under the microscope with stain specific for the bone tissue. So makikita nyo yung osteon. Dito naman yung cancellous bone, tapos ito yung compact bone. Bone formation process can be differentiated into two types. We have the endochondral ossification and the intramembranous ossification type of development. So the distinction between those two types of bone formation depends on whether there is a cartilage model that served as a precursor of the bone, or whether the bone is formed by a simpler method without the intervention of the cartilage precursor. So the bones of our extremities, for example, the humerus and the femur, and also those parts of the axial skeleton that bear the weight, for example, the vertebra, they form through endochondral ossification, while the flat bones like the skull, the mandible, and the clavicle, they generally are derived from intramembranous ossification. So this is how intramembranous ossification will appear under the microscope. So in the intramembranous ossification, the bone formation is initiated by condensation of mesenchymal cells that differentiate into osteoblasts. So The first evidence of intramembranous ossification is usually observed around 8 weeks of human gestation. So, in the embryonic connective tissue or the mesenchyme, there will be noted appearance of spindle-shaped cells or mesenchymal cells, and they will aggregate in specific areas. So the condensation of those cells within the mesenchymal tissue will initiate the process of the intramembranous ossification. So in intramembranous ossification, there will be an ossification center that will appear in the mesenchymal um, connective tissue. So that will consist of aggregates of mesenchymal derived osteoprogenitor cells, and they will differentiate into bone secreting cells, the osteoblasts, and then they will begin to deposit unmineralized bone matrix, which is the osteoid. So this is a more mineralized appearance of the intramembranous ossification. So here, that is the start of the osteoprogenitor cells lining the ossification center. So after the osteoblast will accumulate in the periphery of the ossification center, there will be continuous secretion to release more of the bone matrix, and this ossification center or the osteoid will undergo further mineralization, and the osteoblast will become osteocytes, and the osteocytes in the trapped in the ossification center will further communicate with each other and with the osteoblasts. So there will be a microscopic structure of an immature bone formed, and the newly formed bone tissue appears as an immature bone with thick trabeculae lined by osteoblasts, and inside are the osteocytes here. So there is further growth and remodeling of the bone tissue, and the woven bone or the immature bone will be replaced by a compact bone and a spongy bone in between. So that is how the intramembranous ossification will appear under the microscope. While the endochondral ossification also begin with proliferation and aggregation of mesenchymal cells at the site of the future bone, the endochondral ossification will commence under the influence of a different um, growth factor. So the bone morphogenic proteins and the fibroblast growth factors will trigger the formation of bone under the endochondral ossification. So there are mesenchymal cells that will express type 2 collagen, and those cells will differentiate into chondroblasts that in turn will produce the cartilage matrix. So this appears as a fetal hyaline cartilage model here. So when the cartilage will calcify, there will be a periosteal bone collar that will surround, and that will eventually form the diaphysis. So there is a cartilage model or a miniature version of the future bone, so that will appear So there will be increase in length of this cartilage model, and the increase in length and width is due to addition of cartilage matrix because of because of the new formed chondrocytes. Now, there will be the first sign of ossification here. So that forms a cuff around the cartilage model. And here there will be production of osteoblasts, or the bone forming cells. And then there will be formation of hypertrophic cartilage cells in the cartilage model, and further ossification will occur. So this calcified cartilage matrix will cause apoptosis of the chondrocytes, and there will be more breakdown of the cartilage matrix. And while that is happening, the bony color will appear to be more vascularized here. There is growth of more blood vessels. You can see here. So there is the primary ossification center that forms in the diaphysis, which initially is the periosteal bone collar. Next, there is secondary ossification center, so that will occur at the end of the bone or the epiphyseal areas, and this will contribute to more bone formation, and the bone will replace all the cartilage inside except for the articular cartilage, which will stay at the ends of the bone. And when the epiphyseal plates ossify, that is the end of the endochondral bone formation, or the endochondral ossification. So the endochondral bones, or the endochondral bone growth, will begin in the second trimester of the fetal life, and that will continue up unto early adulthood. So the growth length of the long bones will depend on the presence of the epiphyseal cartilage. So there is what we call as the different zones in the epiphyseal cartilage. So you can see that here. So these zones represent the different layers of ossification in the endochondral ossification. So we have zone of reserve cartilage, zone of proliferation, zone of hypertrophy, zone of calcified cartilage, and zone of ossification. And this is how they appear from the bone when magnified. So this is another illustration of endochondral ossification from the zone of reserve cartilage up to the zone of ossification, and this contains a deeper deeper layers of the bone, including the medullary cavity. So the zone of reserve cartilage, so this is an area where there is no noted cellular proliferation or active matrix production, so reserve cartilage. The zone of proliferation, however, that will be adjacent to the zone of reserve cartilage, going internally to the direction of the diaphysis. So in this zone, the cartilage cells will undergo division and will organize themselves into different columns. And these cells are observed to be larger than those in the reserve zone, and they actively produce collagen. So mainly type 2 and type 11, but mainly type 2. Next, the zone of hypertrophy here. The zone of hypertrophy will contain enlarged cartilage cells, and the cytoplasm of these cells appear clear because of the glycogen that accumulates inside. And the chondrocytes here are still metabolically active, so they continue to secrete type 2 collagen, and the hypertrophic chondrocytes will also secrete different growth factors which will initiate the blood vessel invasion. So the cartilage matrix is compressed to form linear bands in between columns of hypertrophied or hypertrophied cartilage cells. In the zone of the calcified cartilage, these hypertrophied cells will begin to degenerate, and the cartilage matrix will be further calcified. And that calcified cartilage will um, serve as an initial scaffolding for the deposition of the new bone. So that appears the different layers of endochondral ossification. Now, the biology of bone repair can happen either directly after an injury or as a process of bone healing. So we have two major types of bone repair: the direct or primary bone healing and the indirect or secondary bone healing. So the direct bone healing will occur when a fractured bone is surgically stabilized, and the movement is restricted so that the bone is allowed to heal in a more stable process. While in the secondary bone healing, the bone will respond to endochondral and intramembranous bone formation, and those types of bone healing usually happen when there is um, treatment of bone fixation. So you can see in this illustration the process of bone remodeling. So first, there should be a fracture hematoma that will form in the injured part of the bone. Then after that, there will be formation of fibrocartilaginous or callus in that area of bone hematoma, and then that bony callus will harden or ossify, and then there will be resorption of the hardened callus so that the bone is remodeled. So those are the four major steps of bone remodeling. So in here, in the first part, there is formation of several blood vessels within that fracture to supply this area of injury. And then after that, there will be formation of different fibrocartilage substance, and we call that as a procallus or callus tissue. And the macrophage will remove the unnecessary substance or structure here in order to allow regeneration of that bony tissue. So there is formation of primary bone, and there is the formation of the hard callus where the fracture is contained. And then eventually that woven bone is being remodeled as a compact bone in that fracture site. This is another illustration of bone healing process. So the normal bone, when exposed to injury and creates a fracture, there is bone necrosis that will happen, and blood clot formation that will occur. So that is the initial response to injury. So that is the fracture hematoma, as we also saw in the previous slide. Now, there is a formation of granulation tissue, or the pre-callus or the soft callus formation, and that will be deposited in the area where there is injury or bone necrosis. And then that soft callus will be formed as a hard callus, and the osteoprogenitor cells from the periosteum will differentiate into osteoblasts and will begin to deposit new bone here on the outer surface of the callus here. And then they will calcify further and will be replaced. This fibrocartilage will be replaced by bone tissue through endochondral ossification. And then um, here, the hard callus will be transformed into woven bone and will be replaced by spongy bone as resorbed by the osteoclast, so that it can restore the bone into its original shape or close to its original shape. But you can notice callus formation on the surface of the bone. So those are the different features of the bone in terms of structure, in terms of formation, and in terms of bone remodeling or repair. Now, the bone also has physiologic aspects because it serves as the reservoir for calcium in the body. And that calcium can be removed from the bone and be um, included in the circulating level when the calcium in the blood falls below the critical value. So you can note the presence of phosphate and calcium content is also regulated by the bone tissue. So also, when calcium is in excess in the blood, the calcium can be removed from the blood and stored in the bone. And the principal mechanism that governs that calcium and phosphate content can be summarized or can be influenced by two major hormones, the parathyroid hormone and the calcitonin. So the maintenance of the blood calcium is regulated mainly by the parathyroid hormone. So this is secreted by the parathyroid gland, and also calcitonin, which is secreted by the thyroid gland. So the parathyroid hormone will stimulate. So it will stimulate osteocytes and osteoclasts. So The process of stimulation will occur via the rank-L signaling pathway, so they will promote bone resorption, thereby increasing calcium in the blood. While the calcitonin will inhibit bone resorption by inhibiting the effects of parathyroid hormone in the osteoclasts. Thereby, it will lower the calcium level. So this one, it promotes increase of calcium in the blood, and this one, the calcitonin, will inhibit the effect of parathyroid hormone, thus decrease the level of calcium in the blood. So this will target the osteoclast to slow matrix resorption and bone turnover, thereby lowering the blood calcium level. So those are the important hormones that are responsible for the calcium and phosphate content in the blood, which are mediated by bone resorption or inhibition of bone resorption. So that is the physiologic aspect or the metabolic role of the bone in terms of blood calcium level. So thank you for listening to this video lecture about osteogenesis and the different structures of the bone. So all of those are found in your textbook. Thank you.